The methods we've shown so far for using hypothesis tests to compare multiple samples have a powerful use in the analysis of what are called randomized controlled experiments. And that's what we're going to examine in this video. So randomized controlled experiments are quite common, especially in health and medical studies, but they can be used actually anytime you are trying to assess the effectiveness of some treatment or some product, and you'd like to make causal conclusions. So in this setup, in general, you'll start with a group of patients or people who will be in this trial, and you randomly assign them to either the treatment or the control. The treatment group gets some type of intervention, the control group gets nothing, and then you compare the differences in the outcomes. So let's say sample A is your control group, sample B is the treatment group. Since the treatment and control groups are assigned randomly, differences in their outcomes can be compared, and any difference in their outcome could be due to either just chance or to the treatment itself. So if the observed differences are more marked than what we would predict as purely due to chance, and we can test that with a hypothesis test, then we will have evidence of causation. Because of the unbiased assignment of individuals to the treatment and the control groups, differences in the outcomes of the two groups can actually be ascribed to the treatment. Okay, so let's look through this. Let's look at an example of this. This is actually a real study that was done with 31 patients who had low back pain. They were randomized into two groups, either the treatment or control group. The treatment group was given Botox to try to treat their back pain, and the control group was just given normal saline. These were run double blind, so neither the doctors nor the patients knew what group they were in. This was conducted for 8 weeks. And after 8 weeks, they had the patients describe whether or not they had pain relief, and they had a very precise definition used by the researchers as to whether they could say yes or no. So at the end, they ended up with a binary output of yes, I had pain relief, or no, I did not. And the question is, could this difference of 60% versus 12.5% be due just to chance? Or can we say it was due to the treatment? So how we need to think about this is we have to consider the possibility that among the 31 patients in the study, some were probably just going to be better able to recover than others, even without any help from the treatment. And it's possible that an unusually large proportion of such patients got assigned to the treatment group just by chance. So then even if the treatment did nothing more than the saline, the results of the treatment group might look better than those of the control. That's what we're trying to account for by doing a hypothesis test. Okay, so where's the chance in the scenario? Really what I want you to think of is before these patients are randomized into two groups, imagine that there's two possible outcomes for each patient. The outcome that would have happened if they were assigned to the treatment group, and the outcome for that same patient that would have happened if they were assigned to the control group. Those are the two potential outcomes of the patient. I'm having you picture it as just like an imaginary ticket. So out of these 31 people, there are 31 potential treatment outcomes and 31 potential control outcomes. And my question in the hypothesis test part of this is about the distributions of these two sets of 31 outcomes each. Are they the same or are they different? Unfortunately, we don't get to see all of that. We don't know what those full distributions look like. All we get to see is a randomly selected 16 of the potential control outcomes and the treatment outcomes of the remaining 15 patients, right? That's all we get to visualize. So if you think of this in terms of comparing two samples, our question is the distribution of the 31 treatment values, including the unknown ones, right? So this whole distribution here, is that distribution, even though I can't see it all, is that the same as this distribution? Could they have come from the same original distribution. So here's a picture of this. All the potential treatment scores, all the potential control are these two, and I have them in the cloud because we don't know what they look like. They're unknown. Are those two the same? In that sense, we can think of what we actually observe as just a sample from this distribution, and actually observe a sample as just from this cloud distribution. So now the setup looks very similar to our previous examples where we just took 2 random samples. So our null in this case is going to be the distribution of all 31 potential treatment outcomes is the same as that of all 31 potential control outcomes. The difference in the 2 samples is just due to chance. And we can summarize this. Usually what you'll hear being said in this is a quicker, the treatment has no effect as a summary. My alternative is no, there is some effect. It is standard, and especially in medical studies, not to choose a direction. So we are just going to test that the treatment does something different than the control. So I'm not specifying that the treatment helps, just that it's different. This is standard because it doesn't prejudge the way the results might go. But you're welcome to run a test for whether the treatment does better than the control. You would just need to adjust your test statistic accordingly. Now let's pop over to the notebook to go through the steps in this process. We can notice that we've set this up in the same way that we set up our A/B tests. So go to the A/B testing notebook, and then we're going to scroll down to randomized control trials. This has a description of the experiment as well as a link to the actual study if you're interested in reading. But let's load in the data. This is the data of the results where patients either reported a 0 with no pain relief or a 1 with pain relief. So that's how we have the data output here. So the null and the alternative is what we just stated in the slides, and it's standard with medical studies to test at a significance level of 1%, so that's what we'll use here for our significance level. Now, when it comes to choosing a test statistic, looking at the form of the data, we have binary data. So really, I'm interested in seeing if there's a difference in these 2 distributions between the control and the treatment. Because the control and treatment groups only have 2 possible outcomes, 0 or 1, this naturally leads us to think we could use TVD, the total variation distance, as a way of measuring whether those 2 distributions are similar or not. And so that's a very valid test statistic, and that's what we're going to use. I'm just going to point out there's actually 2 other ways to formulate the TVD in this situation because of how we have the data. If you think of also just wanting the absolute difference in the proportion of successes or the proportion of ones, that will be equivalent to the TVD because I'm just going to be looking at the difference in the ones, not the differences in the zeros. The TVD accounts for that by dividing by 2. So these are equivalent. And because I have binary data, it turns out that the proportion of ones in a given group is actually equal to the mean of the data from that group. Because I'm adding together a bunch of zeros and ones, dividing by the total number, the mean will be equivalent to the proportion of ones. So that's actually how I'm going to code it here. But I just want you to realize that's actually equivalent to the TVD. So you could use our TVD function just as easily here. All right, so let's calculate our observed test statistic for this. First, I'll show you in the grouping, right? So in the control group, only 2 out of the 16 reported relief, whereas 9 out of the 15 in the treatment reported relief. So those are the 2 proportions. We're going to take the absolute value of their difference. We could just do that. We can just write our own code for this, but I'll point out that we actually have done this above when we were doing our A/B test in our difference of mean functions using absolute value as true. So that's what I'm going to use here. But if you want to do it manually, it would be this. Now, how do we actually simulate this test statistic? This is exactly where permutations come back into play because I'm trying to test whether or not these the results that I saw, these binary outcomes, could have just come from the same distribution, in which case the labels of control versus treatment, I could just shuffle. It shouldn't matter. So that's what we're going to do. We're going to shuffle the control versus treatment labels and output the results. So let's do one full simulated difference here. I'm using that function we wrote above in the A/B test example just because we already had it in this notebook. And again, it's because it's easy for you to visualize what's happening. I'm keeping the results constant. I'm shuffling whether it's control versus treatment, and then I'm going to calculate the proportion of ones in my new shuffled label of treatment versus control. So that's what's happening here. I'm looking at the absolute value of the difference between the one proportions in my shuffled treatment, shuffled control. And if I did it again, I'm going to get a different simulated difference, right? So now I get 0.08. So we're going to repeat this and plot the empirical histogram of the test statistic. I will point out this next piece of code is going to take quite a bit of time to run because I'm going to run this 100,000 times. I will point out below in a minute why we're going to do so many repetitions here. In the past, we've often just done 10,000 and been fine, but we're going to see in a minute why we needed many more in this case to get to see. We wanted to make sure that our empirical distribution of the test statistic has fully converged as far as possible, or to a very good approximation of the actual distribution of the test statistic. So go ahead and let this run for a bit. Here's the result after our simulation finishes. And so we can see that our observed test statistic of 0.475 is actually pretty far out here in the tail. And to see the actual p-value, which would be the area underneath this in the direction of the alternative, right? So to the right here, I'm going to see out of all the simulated differences, how many of them were greater than or equal to my observed difference divided by the 100,000 that I did. I get a p-value of 0.009. So one of the reasons that I wanted us to do so many simulations here is because our cutoff is 0.01 and the actual p-value is very close to that cutoff, it's just underneath. If we hadn't done enough simulations here, sometimes our empirical p-value would be popping above 0.01. Sometimes it would be below. This is actually the correct one. And we're going to see that. I have a little demo down below here. Scroll down to the bottom here. And I ran this. This code takes a very long time to run, so you don't need to run it yourself. But this is just to show the fact that our empirical p-values are affected by the number of simulations that we run. And when you have a p-value that's very close to your cutoff, you want to make sure that your simulation size is large enough so that you've basically converged as close as you can to the theoretical value. So here you can see the difference of what happens. I do 1,000, 10,000, 20,000, and then 100,000 simulations. And I just kept track of the p-values for these different rounds of the simulation, and we're going to plot it. So here, this is a stacked bar chart, but just to let you see that your 100,000 simulations, here's the p-value, right, for our observed test statistic. And so it's converging to less than 0.01. But if I hadn't done enough simulations, if I had just done 1,000, you can see, or even sometimes 10,000 or 20,000, I may end up with some values here. You can see the pink ones here, where I'm above my cutoff. I'm above 0.01, just because this empirical p-value hasn't converged to the correct value. So this was an example. We were very close in the actual difference between the theoretical p-value and the cutoff we were using. So you just need to do a lot of simulations to make sure your empirical p-value has converged. So this is less than 0.01, and the actual study confirms this. It shows the p-value of 0.009, which is actually what we get here. Okay, so let's go back to the slides to make our conclusions. So let's summarize what we just did in the Jupyter Notebook. In particular, we were testing whether multiple samples look like random draws from the same distribution. But we were very specifically testing this about these 31 potential treatment versus 31 potential control outcomes. We found that the data is consistent with the alternative, that the distribution of the 31 potential treatment outcomes is not the same as that of the 31 potential control outcomes. And since our p-value was less than 0.01, we can say this result is highly statistically significant. We can actually go further with what we can say in this situation because of how we set up the trial. When you set up a randomized control trial and your treatment and control groups are selected at random, any difference in the outcomes is either due to chance or the treatment. Our hypothesis test told us that it's very unlikely the difference was due to just chance. We rejected that null, which leaves us the ability to say that the difference was due to the treatment. In fact, we can make a causal conclusion. We can say the treatment causes the difference. This is because the random assignment of patients that we did ensures there's no confounding variable that could affect the conclusion of causality. It would have shown up in our hypothesis test step here, if that were the case. Now, the downside to this is that this is only a conclusion about the 31 patients in the study. So in order to make conclusions in general with this type of data and this type of question, you have to do more and larger randomized control trials. There actually was a meta-analysis conducted on this particular treatment, and the researchers found, unfortunately, there's only 3 randomized control trials done so far that fit scientifically sound practices. And so from those 3 so far, they did not find high enough evidence that these injections improved pain, function, or both better than saline injections. This really just indicates at this point further research is necessary, and or future randomized control trials would be necessary before we conclude with more confidence that this is an effective treatment. So this just points out really the complexity that goes into actually releasing a new drug or a new treatment. It's more than just one successful randomized control trial. Now, I want to make a comparison here. Anytime we're trying to run a hypothesis test about whether 2 samples came from the same underlying distribution, we either are going to have data that has been observationally gathered or a randomized control experiment. In this case, again, we're assuming that we're testing 2 samples to see whether or not they came from the same distribution. So we are going to have the same underlying mathematical process. We'll be using a permutation test, shuffling labels to simulate the null. The conclusions are just what's different. If we end up getting a significant result from an observational sample using a hypothesis test like this, the most that we can conclude is just there's some association between the variables. In a randomized control experiment, I can say not only association, but causation. So I can say, yes, that Botox was not only associated with pain relief, but it caused it, again, for those 31 members of the trial. So this gives us a good, quick insight and taste of how hypothesis tests can be useful in the context of randomized control trials.